Hi, and welcome to the Computer Architecture Podcast, a show that brings you closer to cutting edge work in computer architecture and the remarkable people behind it. We are your hosts. I'm Suvinay Subramanian.
And I'm Lisa Xu. Today we have with us Professor Yungang Bao, who is a professor of the Institute of Computing Technology in the Chinese Academy of Sciences and the Deputy Director of ICT-CAS. Professor Bao founded the China RISC-V Alliance, CRVA, and serves as the Secretary General of CRVA. His research interests include open source hardware and agile chip design, data center architecture, and memory systems. Professor Bao's contributions include developing the PARSEC 3.0 benchmark suite, which has been adopted by leading industry players in China, like Alibaba and Huawei, the labeled von Neumann paradigm to enable a software-defined cloud, hybrid memory trace tool, or HMTT, and partition-based DMA cache. He was awarded the CCF-Intel Young Faculty Award, was the winner of the CCF-IEEE CS Young Computer Scientist Award, and received China's national honor for youth under 40. Today, he's here to talk to us about the state of hyperscale cloud in China, open source hardware, and his efforts in revamping computer architecture education.
A quick disclaimer that all views shared on the show are the opinions of individuals and do not reflect the views of the organizations they work for.
Yungang, welcome to the podcast. We're so happy to have you.
Thank you for inviting me. I'm very happy to having me. Thank you.
Yeah, we're so excited to have you too. I think so. What's getting you up in the morning these days? What's making you excited?
Yeah, today is Saturday, and the next day actually Sunday, but it's a working day. We accepted to the May 1st. There will be 5-day holidays. Every day it seems like we are approaching the 5-day holidays.
Gotcha. So what's making you excited is 5 days off.
Yes.
So yeah, well, that would make me excited too. So how about on the work front? I think one of the reasons why we were really excited to have you on the show today was because over here in sort of the Western Hemisphere, there's a lot of cloud stuff, and although news is dominated by like other hyperscalers in the West, like Microsoft, Facebook, Google. And then we hear about Alibaba, and we hear about all the companies out in China, but and then we see the papers that get submitted to ISCA and published in ISCA and other top venues, but it is far away. So like one of the reasons we're excited to talk to you today is just like to get your views on whether or not they're facing parallel problems, or what the opportunities are over there, and what the kind of culture and thought process around how to manage a hyperscale cloud is for some of these major Chinese companies.
Yeah, so actually in China, probably we don't see hypercloud. So actually we talk more about like internet companies. Yeah, since actually those internet companies, they consume a lot of data center servers. Yeah, basically there are two phases for those internet companies growth. In the first phase, actually, I think is that before 2010, there were 3 major internet companies called BAT, just you mentioned, Baidu, Alibaba, and Tencent. Yeah, those 3, today they are still giants company in China. But there are also some new company rose over the past decade. For example, like Jingdong, JD, TMD. T is we see the ByteDance actually used to be the Toutiao, yeah, and later changed to name to ByteDance. And there are also another company called Meituan M in the Didi. Actually, this is a competitor with with Uber. Those are new internet companies in China. Yeah, those companies together, I think I used to see a report on the top 20 internet companies of the world in terms of the market capacity. I think there are 12 in the US and 8 in China. Yeah, so those are internet companies. They consumed a lot of servers, I did some homework on how many servers or computation capacity they are consuming now. So I see like last year in China. So the China server market, the revenue is 25 billion US dollar. Yeah, accounts for like 1/4 of the global revenue, and the shipment volume is it's actually 3.9 million servers in China were shipped last year. The global market is about like 14 million.
So that is very significant. And it's interesting that you characterize it in terms of internet companies and like sort of server consumption. So I guess my question to you is because like maybe it's because I work for Microsoft and Suvene works for Google, where like in my mind there's cloud, there's public cloud, private cloud, and then a place like Meta where they run their own servers because they have this massive presence and they have a lot of demand. So for some of these newer internet companies that you described, like for example Didi, right? Didi, the actual product is a competitor to you, so the actual product is these rides, but of course it needs to be backed by a ton of server capacity, as you've sort of described. So are these rising new internet companies in China building their own data centers, or are they sort of renting data center capacity from another internet company? Like how is the ecosystem out there?
Yeah, for those companies just mentioned, so those companies, they actually prefer to build their own data centers. Yeah, for example, like Alibaba, like Tencent, they have many sites, data center sites all over the country. Yeah, some in like around Beijing, some in Western China. Recently the Chinese government encouraged companies to build data centers in Western China. Since in this area there are enough like power, electricity. So it's easy to get a power. Yeah, for Eastern China, since the electricity is more expensive than Western China. So many companies they will choose some places to build their own data center. There are also some other companies, middle-size, we say middle-size, company or small-size startups, and they usually use public clouds. And for example, like Alibaba has its own cloud, public cloud. So, and I think they ranked like number 4 or in global market. Yeah, number 1 is Amazon and Microsoft Azure. Besides Alibaba, there are also other public cloud companies. For example, like actually Huawei also provides a cloud service. Tencent is providing cloud service. Actually, most this is kind of different since Tencent has its own ecosystem. Like for example, WeChat. Yeah, on WeChat there are a lot of like light. We say like we call it light program. This is just like small apps. Yeah, can be installed on WeChat. So on the WeChat platform, there are many startups, many small companies. They build their own light apps, and those light apps can run on WeChat. And so Tencent provides computation service for them. Yeah, this is kind of different levels of cloud services.
Got it. Yeah, I mean, that's a fascinating overview. Thanks a lot for that summary. Just donning my computer architecture hat on, I think there are several themes over here. I'll pick up on one of them, which is the workloads and the applications. You talked about these cloud providers. Of course, there are people like Alibaba who serve their own products and so on. But for Tencent, which has the WeChat app or ecosystem, a lot of people essentially build applications or tiny applications on top of this particular platform. So from a workload standpoint, like how do you view the cloud ecosystem in China, especially with this diversity of workloads and also this control of the ecosystem? Often when we, for example, when Google runs machine learning workloads, we control the stack all the way through to TensorFlow, which allows us to do a lot of optimizations across different layers of the stack. I was just wondering, given the distribution of the workloads and the kind of ecosystems available in China from a computer architecture perspective? Like, does it either open up interesting new opportunities? Are there different attributes or characteristics of these applications for the cloud ecosystem that you see in China?
Yeah, I think for more and more data centers run AI-related workloads. I saw a data that most internet companies, they consume a large amount of their servers are running AI-related workloads. Yeah. So for example, they do for Alibaba, they use AI to recommend things or stuff for consumers. Yeah. And for like ByteDance, yeah, ByteDance, they and TikTok in the US and Douyin in China. So they consume a lot of AI. They need a lot of AI power, computation power for AI workload. Since a lot of like make people look beautiful, more beautiful. Like there are a lot of they have a lot of very small gadgets to make the video look better. Yeah, look beautiful.
It sounded like almost like you were saying that, if you were to look, because as Suvene pointed out, it does seem like you have potential bifurcation of workloads, where if you're going to say like, okay, I want to make the hardware better in order to serve these workloads, that might be different because, this company has their own stack and their whole kind of sort of like closed system. This other company has their own closed system. This other company has their own closed system. And so then, then how do you make the hardware better for all of them? But it sounded like what you were saying is that you could sort of broadly characterize and generalize that a lot of them are running AI workloads. And between these two kinds of AI workloads, or within the AI workloads, there's like potentially even another classification where some of them are recommendation, where it's like, hey, let's make people look at these videos or recommend these products. And then the other is sort of almost like, I don't know if there's a term for this, like smart filtering, where like we can make the video better and improve the light background or make people's eyes bigger, or like cat filters or something like that. So then that kind of stuff is probably a different kind of underlying AI substrate than recommendation models. If you were a hardware person trying to kind of attack the China market, would you say then like, okay, let's focus on recommendation models, or let's focus on multimedia filters or something like that? Like, is that essentially what you're observing?
So this is probably challenging for building a general purpose computer architecture for those diverse workloads. So that is why for many Chinese internet company, they start to build their own chips. Yeah, GPU is still the major computation power for the general AI workloads, but for some specific workloads, and so many companies they prefer to build their own accelerators. Yeah, so you will see like Alibaba is building its own chip. In the ByteDance, they invested some AI accelerator companies to accelerate their workloads. So it's every company has its own requirements on computer architecture. In the future, probably the better way is to provide Agile chip design, chip development methodology. Yeah, since then it's easy for us to tackle such diverse requirements. So that is why I choose to open source and Agile design, hardware design, this direction.
Yeah, certainly. I mean, that's a very pertinent point. If we look at the chip design lifecycle, like the design costs are pretty high, and sort of bootstrapping a new chip design tends to be a pretty labor-intensive and time-consuming effort. So maybe this is a good point to sort of talk about your efforts. You've been building an open source RISC-V based processor, as you mentioned. So can you tell us about the effort, the current state? What have your learnings been during that entire process?
We launched the Xiangshan project 2 years ago in 2020, but actually we have made we prepare for this project almost since like 2015. Yeah, so this is a long journey to this project. So I used to run a project called Labeled Compute Architecture, and we build a simulator, we build a FPGA, and we publish paper on us+, but we hope to build a real chip in 2015. Yeah, actually I did a survey on all potential or all feasible solutions. For example, like x86 and ARM chips, and I didn't figure out a feasible solution. And finally, I found, well, RISC-V and the Rocket chip is just the solution, the right solution for us. And then we tend to use Rocket to build the labeled compute architecture prototype chips. Yeah. After we choosing the RISC-V and the Rocket chip, actually we made two decisions. One decision is using chisel rather than Verilog. Yeah, but not everyone supported this decision. Even in my group, we did a set of experiments to compare Verilog and chisel. So the experiments were divided into two phases. One phase is I asked two guys to complete to level 2 cache and to integrate into the Rocket chip. And one is a senior student, undergraduate. Another actually is an engineer. He is good at actually he is good at cache and has studied OpenSpark T1 cache and the Xilinx the cache. He studied those caches. And okay, the senior student undergraduates use the chisel, and the engineer use the Verilog. The result is that the undergraduate only took 3 days to complete the work. Yeah, and integrate the cache into Rocket chip, and then it can run like Linux even with the DMA. So it's fantastic. But for the engineer, he actually spent 6 weeks to finish the L2 cache, and it will integrate into the Rocket chip. But there were still some bugs. Yeah. So this is it's a very impressive comparison, and so there are different. Also, the lines of codes for chisel only one fifth of lines of codes of Verilog. So this is the productivity is a huge different. But the engineer refused to accept this result. Yeah, he said his design is better. His design is better in terms of frequency, power, and area. Yeah. So then I asked another senior student, also undergraduate student. He never learned chisel, but he can write Verilog code. So I asked him to rewrite the engineer's Verilog codes into actually translate the Verilog codes into chisel, and then pass the verification program of the written by the engineer. And he took about 1 week to finish this task, and we will see that all the data, the PPA actually most of the PPA is better than the Verilog version, the engineers. So that is quite impressive for us. We actually, of course, this is done on FPGA. It's not on the ASIC flow. But anyway, we can see that the chisel can do quite good work, at least for this fasting prototyping. Yeah, Actually, I gave a talk on the visioning workshop in 2019 on ISCA, the Siga Arch visioning workshop. Yeah, in China, many companies they start to pay attention to chisel, and some companies they form a team to build chisel libraries and to help accelerate the development cycles. So this is our experiments. Yeah. Then and in our group, everyone was convinced to use chisel. But anyway, there are still a lot of concerns about chisel, since people will say that this is only small module, like L2 cache. It's just a module. There's no evidence or no case study to show that chisel we can use chisel to build a complex like high performance processors. The next is our next decision is, so we decided to use chisel to build a high performance the RISC-V CPU core. This is the Xiangshan. The Xiangshan project, actually we target actually high end of ARM processors, but anyway, it's still far away from ARM chip. But we hope in the future we can approach that target. So the first version is actually we taped out last year. It was in 28 nanometers, and it can run 1 gigahertz. The chip was back this February, and it brought up successfully and we finished all test in 3 weeks. Yeah, everything actually seems quite good. And with DDR4 1600, yeah, DDR is not that fast. So the chip can run 1 gigahertz, and we run all the spec CPU 2006 and get the score. The score is 7 per gigahertz. Yeah, it's not that it's actually if we don't we don't look at like power or area, this performance is similar to ARM Cortex A73. But anyway, Cortex A73 is much better in terms of power, yeah, and also frequency is much higher than the first generation of the Xiangshan. And now we are working on the second generation. This will tape out next month, yeah, in this May. And the second generation, now the frequency can reach 2 gigahertz in 14 nanometer technology. The performance is 10 points per gigahertz for spec CPU 2006. This is the second generation. Yeah, you are right. Just you mentioned that actually the third generation is ongoing. So every year there will be a new version of Xiangshan.
Right, that's a fascinating journey, like from your early observations that it's difficult to translate your ideas into actual chips, into having your second version of the chip out and the third version in design is quite fascinating. I think there were a few takeaways for me from that entire experience, starting from the early days when you had to bootstrap this and figure out, okay, how do we actually do this? What's the right set of tools that you can use to build this? Sort of using the experiences of your undergrad students to actually convince people that it's possible to be productive, and it's actually the chip designer that matters more than the tool itself. The tool is quite productive. I think your early experience, you showed that the second undergraduate student was able to take the Verilog that the designer was able to implement in Verilog and translate those ideas into Chisel, and therefore get a very performant design point for the L2 cache, and sort of taking it from that initial prototype all the way through to a complete processor end-to-end in RISC-V that actually works and is competitive on certain metrics with some of the ARM processors is quite fascinating. So maybe I can ask you, like, what's next on the horizon for this project, right? Like, so you started with an L2 cache to a processor. Now you have the second generation out in the lab tested, and looks like you have the third generation as well coming out. How do you see this being used? What's your hope for how these kind of open source but yet high performance processors built using these open source tools and that also improve developer productivity. How do you see these being used in the future?
Yeah, I think from our perspective, the main merits of Xiangshan project is not only the Xiangshan, the processor itself, but also the framework, the chip development framework. So actually, there are already many other frameworks like ChipYard from Berkeley, like Open Python from Princeton, like Black Parrot from University of Washington, and also the ChipKit from Harvard, that Brooks group. So there are many other frameworks. I think the frameworks of Xiangshan is has its own features. It's actually we focus more on not only agile design but also agile verification. Actually, we build a bunch of tools to support agile verification. A bunch of tools, there are more than like 10 tools for verification. So what we needed to address is when we make a modification or modify a design, for example, like currently we have the second generation, then we needed to do the third to build the third generation. We have to we will make a lot of modification based on the second generation. But we needed to address how to verify its correctness. How do we know the modification is correct? And we also needed to get the performance changes. What's the impact of the modification on performance? Since these two issues are very important for agile development. Otherwise, we can not just design is actually is easy. You since you are doing TPU, you know many verification actually is time consuming, and also we need a lot of engineering work. But we figured out some interesting. We have some interesting observations to do agile verification based on Chisel. Actually, Chisel is a very good language for agile verification, since it is just like the LLVM. So we can do many like paths. Here is not fast transform can be insert into Chisel. So recently there are also new IR based on the ML IR. For example, we can write our own transform based on those this IR. And for example, we have built a tool that is able to translate waveforms into Chisel code. So when you are watching the waveform, you will see the events. What Chisel code is related to this waveform events. So it's this kind of a tool actually can help us to do like agile debugging, agile verification. So I think Chisel actually is a very good framework to do a lot of extension for agile verification.
I think this is really interesting because I think in the sort of the history of our field, we introduce tools that sort of allow people to move further and further away from the lowest low levels of the machine. And so that sort of enables the scaling of, in some ways, human capital. So more people are able to do a good job. But the key is, as you say, a framework that's able to sort of make things easier for the users on the top, but still produce quality in the bottom. And that production of quality on the bottom means like you can attack the problem in this framework layer by making sure that, and continually improving it. So similar to like compilers, right? So everybody used to write an assembly. It means you had to have the machine in your head, but then if you continually attack the compiler problem, then you can, continually improve the size or the quality of the machine code underneath, right? And so I think what you said right there, because when I first heard about Chisel many years ago, one of the things that you would hear about is just like impossible to debug, right? Because now you introduced a layer between the final user and the bottom level, and you can't go in and figure out what went wrong. And if you have an idea yourself, like maybe the engineer did, an idea of what you want the bottom level to look like, and you can't actually make it do it because it's too soft, the layer in between, then it makes it difficult. So that thing that you just said there, where you're actually able to watch the waveforms go by and have it go, like, be pinpointed back to the Chisel code that is sort of instigating that waveform, like if this is the part of the code that's being run right now, that seems like a major leap forward that enables this translation between what the user is doing and what is like being produced at the very bottom layer. So I think one thing you mentioned before was that now people are doing a lot of work on Chisel itself to make that better, which is, I think, a great way to enable that framework to continue to improve and continue to scale the ability of humans at the top layer to produce what they want. So when you have students come in, like, are you more targeted at them working on the Chisel side so that they can see this translation between the top and the bottom, or are you having more working on, as users and doing design?
Yeah, this is a very good question. So that is actually how we train our students. So it's not easy for a junior student to participate in the Xiangshan project directly. Yeah, it's the project is still quite large for them to understand, to investigate, to modify. Yeah, before students joining in the Xiangshan project, we will ask them to participate in the one student, one chip project. So this is the one student, one chip initiative. So we will provide the opportunity for them to build a real chip. This is a small real chip. But after this training, then they will be good at using Chisel, since we ask them to use Chisel to build the small chip. And we also provide the tape-out opportunity, the channel for them. And so every student can get their real chip. When they want to get a real chip, they need to pass some verification, or pass some tests. Their design needed to be able to run a real-time operating system, and needed to be integrated into an SoC. Some of those students assigned the physical design tasks. So this is the whole process of a chip development, from like architecture design, SoC integration, and physical design, all are done by students. Once their design passed the tests, and then their design will be taped out. Currently, we are using 110 nanometer technology. It's not that expensive. We use a framework to integrate all those CPU cores built by the students into one die. So in one die, there are like 10 CPU cores. This is a multi-core, but heterogeneous. This is really multi-heterogeneous core. It's totally different designs, but they share bus. They share the IOs, and then they can, when the chip is back, they can enable their own core and disable others' core, and the chip can run. So the cost can be reduced to almost currently it's like $3,000 per student. It's quite cheap.
That's amazing. That's super cool. And is that something where the one student, one chip project, is that available only to students like who are at ICT, or is it sort of a nationwide effort, or how does that work?
For the first year, it's only there were only ICT students. This is the University of Chinese academic science, we call UCAS. Yeah, there were 5 undergrad students participating into the project. There were only 5 students, and the next year there were 11. There were 11 undergraduates from 5 universities, and then for the third year, is the number is actually skyrocketed, and there were 760 students all over the country from 168 universities. Students they applied for one student one chip initiative, including 23 universities from outside China. Yeah, like some university in the US. And now currently we are running the fourth year. So currently we have already the applications are already larger than 1,200. Yeah, from more than 200 universities. So this is it's become a nationwide initiative, and many companies they donate funding for us. So we also use a way to, since there are like so many students apply for the project, so we need a lot of TA. We figured out a way that the third year, those students, they perform very well, and in the third year become the TAs of the fourth year students. Yeah, so then we recruit about 30 to 50 TAs from the last term to serve as a TA for the next term. So the whole initiative can run at a very low expense.
This is a fascinating experiment. I'm intrigued by so many different aspects of it, and it sounds like a very valuable experience for students as well. Because they learn by doing, they get a more hands-on approach to understanding the concepts, to seeing it actually taped out. And you sort of talked about the pipeline where they start off as applying to sort of build the chip and sort of experiment with their ideas, and then in the following year they become TAs and sort of shepherd these ideas for the next batch of students as well. So overall, this entire pipeline is extremely fascinating, and I'm curious to hear about all the other learnings that you've had through this experiment. But maybe this is also a good time to sort of wind the clocks back a little bit and understand your journey, sort of how you came to ICT, how you got interested in computer architecture, sort of how you see the state of the ecosystem as well, having been in this field for a while now.
So my first time of seeing computer actually was in middle school. Yeah, I think that is like 1993. It's in my middle school. So it's I was born in Eastern China. So that time, a company owner, an entrepreneur, he donated 20 computers to our school. Yeah, 20. I think it's 286. Yeah, it's 286 computers. So I become kind of I think, oh, okay, this is what my whole career. Yes. So actually, you can see that I probably already made a decision of my career since I was a middle school student, and then I got my first home computer in 1994, and this is, I still remember, this is a CRISC CPU. This is a 486 Series 486 CPU, and I write my first program. But at that time, since I was in a small town, there's nobody can teach me programming. At that time, we in the school only learn like basic Foxbase, Foxbase database. I still remember. Yeah. And when I entered the school, the university, the Nanjing University, I was I think I found that I was good at like system courses. So, but I still don't know. I still didn't know how to do system research at that time. Since you know my undergraduate thesis is still on like natural language processing. Yeah, I found my research topic. I finally dived into computer architecture since I was entering ICT. So ICT is there are a lot of famous system project in China, like the Dawning, the supercomputer. This is used to be the fastest supercomputer in China, and the Longshan, the CPU. Actually, this is China's first general purpose CPU in China. And also, there are many spin-off startups like Lenovo is a spin-off of ICT. Yeah. So, and I found that wow, this is the right place. So I found then in ICT I learned a lot of computer architectural knowledge, and I also did my first project. This is the HMTT. This is actually the memory monitoring toolkit. It is it's plugged on the DIMM slot and can track all memory bus signals and can be translated into virtual address. Yeah, we actually do like a hard OS and the memory system co-design to translate the physical address into virtual address and to identify processors memory behavior. Yeah, this tool is still work right now. Now it can support DDR4, and also last year actually Microsoft also bought a set of HMTT 2 years ago. It's so this is my first research project, and later actually in 2010, after my PhD, I went to Princeton University and working with Professor Kelly on PARSEC. I think that is actually opened my eyes on computer architecture. I knew more people, more pioneers in computer architecture, and I start to know many like Lisa. Yeah, I knew many friends in the area. So actually, this has also given me a lot of new opportunities, and also there are a lot of people helped me, encouraged me, and also inspired me a lot. So this is my journey of to the computer architecture. Yeah, so I appreciate it all of those who helped me.
That's a great story, because I think from all the folks that I've interacted in the field, there's like a huge range of people saying like, I saw a computer and I fell in love, or like I showed up in college and I didn't know anything and then I fell in love. And so but either way, everybody falls in love, or everybody that I know of in our field who like really has an affection for our sort of field of study and succeeds in, is because they're really passionate about it. And it's cool that you sort of like through the generosity of this one entrepreneur sort of like set the course of your life, when you were a child. So that's pretty cool. And you're sort of taking it full circle now where, you've instituted this program that is sort of not only nationwide, potentially internationally, giving lots and lots of students the opportunity to do something cool that, I didn't do in school myself. And like, I almost wish like, oh man, I wish I was in school now and I could do that too. So that's very awesome. So with this really, this kind of tandem effort that you have with building an open source high performance processor, with RISC-V, and B, like using that as a vehicle to develop frameworks to enable, enable more productivity and teach students. So for a long time, every year we have a lot of Chinese grad students or Chinese students come into the United States, come to American universities to learn the craft of computer architecture. And so now, with this homegrown effort out there, are you finding that you have A, students staying more, and B, students internationally coming to Chinese universities to study computer architecture? And then sort of a little bit as a tongue-in-cheek question, do you guys use Patterson and Hennessy?
Yeah, so actually you will see that for the second term of a one student, one chip project, so actually we have one student after he finished the task, and he applied for the PhD program from MIT, and finally he got an offer. And another student applied for University of Toronto, and he also got the offer, but finally he didn't. He failed to go due to the pandemic and the visa issue. Yeah, so he stayed in China. But you will see that actually this that what you mentioned, A and B, for me they are combined together. The first year of the 1S 1C initiative, all five students become the major force of the Xiangshan project. And for the second year, some students going abroad, and some also many students stay in China and join in the Xiangshan project. So I think this is I think for the one student one chip project, this is open. We encourage students to go abroad and to learn more expertise from all over the world. Yeah, we encourage them to do that. Yeah, but for the other side, so you mean are there any like international students returning back to China? Yeah, so it's we will see some students they are returning, since there are more and more opportunities and job. There are a lot of jobs. So in China, so that's what I mentioned. Many internet companies they start to build chips. Yeah, so a lot of positions, jobs in the market. So and they can pay quite good. Yeah.
I was actually more asking, so like the United States used to be like a very big sink for students all over the world. And then now, and so I guess I was more wondering whether you were detecting that China, because of some of these things, was also sourcing students, non-Chinese students from outside of the country, like whether, say, European students or Turkish students or even American students or Canadian students are actually applying to Chinese universities. Because, I don't live in China, so I sort of always imagine Chinese universities being filled with Chinese people, but maybe that's not the case, and I'm just curious.
Yeah, you are right. Currently, most students are still Chinese students. It seems like more international students like to go to the US and to, since there it seems like have good opportunities in the like teaching skills and also many other like environments. Oh yeah, but for Chinese students, I think it seems like in China there are also more and more opportunities. Yeah, so since this is also attraction of students abroad.
I did want to ask, like, what textbook do you guys use? Like, do you guys, like the rest of the, yeah.
I forgot that question.
Yeah.
Yeah, we do use the Partition John Hennessy's textbook for graduate students, and for undergraduates. So usually we have in many universities has it's the textbook in written in Chinese. Yeah. And for example, there are already some textbook on RISC-V, and Professor John Hopcroft from Cornell, actually he helped a lot actually to guiding or to instruct Chinese universities to write textbooks. Yeah. So we recently in China launched the 1.1 or 101 project. This means for 10 courses, we want to write a good textbook for 10 courses with the efforts of with the joint efforts of many universities. So there are like 33 universities. Each universities there will be at least one faculty to participate in the 101 project to help refine the textbooks for 10 basic courses of computer science. Yeah,
that's great. Yeah. Speaking of students and opportunities, any words of wisdom or advice that you would have to students today, or just other listeners to this podcast as well?
My suggestion is just like learning by doing. So concept is important, but we also need to put our hand dirty. Yeah. So and to learn by doing. If we can do more practice, we can master the knowledge more comprehensive. Yeah. So I think this is always true. I hope those students who are exciting with physical things, yeah, just don't be just dive himself into the computer architecture field. Yeah.
Awesome. Well, that was really wonderful. I super enjoyed talking with you today, Yungang, and I'm sure I speak for Suvene too, and that this is just like a really interesting session to hear about these great initiatives that you're putting forth. And it's been a total pleasure to speak to you today. Thank you so much for joining us.
Thank you for having me. Thank you very much. Yeah.
Yeah, thank you, Professor Yungang Bao. It was an absolute delight talking to you. And to our listeners, thank you for being with us on the Computer Architecture Podcast. Till next time, it's goodbye from us.